We're going to have our first panel, Ocean Data 2.0, the journey from abstract science to powerful solutions. And our order of speakers, we're going to have Dr. Nathalie Zilberman. Did I say that right? Good. And then Chao. And then Paul, are you here? Yes. Paul. We're good to see you again. And Leif will follow that. And I've got Nathalie, go ahead and come on up here. Nathalie's a researcher from the Integrated Oceanography Division and Climate Atmospheric Science and Physical Oceanography Division here at Scripps Institution of Oceanography. Your slides are there. And I will sit down here with the panel. Take it away.
Okay. Thanks you all for being here today. So in this presentation, I'm just going to give an introduction of the transition and evolution of the ocean observing system. I will then talk about the Argo program and planned expansions of Argo, and then I will finish off with the summaries of Argo's keys to success. So in this slide, I'm showing a few things. First, the bottom panel is showing a summary of all the observations that are currently available for studying ocean observing. And you can see that it's a blend of remotely sensed observation and in situ observations. Some of them are floats, so gliders, buoys, and ships. And what's interesting is that in the evolution of the ocean observing is this transition from observations that were collected mostly from ships to autonomous robots that you can just deploy and they do their thing for up to 10 years, collect data and transmit data to satellites. Most of the observations that are currently available, and you can see this strong increase in the observations available in the top right panel is coming from Argo floats and ocean gliders. The top left panel is showing another interesting fact is that you can see a transition from blue to red in the upper 2,000 meters, and that's largely contributed for by Argo. But underneath, below 2,000 meters, it's mostly blue, indicating that there's not much observations and that the deep ocean is largely unmeasured. So the Argo data set is the main source for subsurface ocean observation and is routinely used in weather and climate prediction. This map is showing the current locations of the floats that are active. They are color-coded by countries. There are 30 nations that are currently contributing to Argo. So Argo is an international program. So the bottom figure is showing a typical cycle from an Argo float. The float descends to parking depth, where it drifts for about 9 days. Then it descends to maximum depth, that is either 2,000 meters or 4,000 to 6,000 meters for the deep floats. And then measure temperature and salinity on the way up, transmits to satellite, and then start a new cycle. So something that is very important for Argo is that the data is available without any restrictions. And I'm not only talking about temperature and salinity data, but also engineering data and metadata so that you know how good the data is and how well the float is doing. And because of this availability of the Argo data set, there's a very high number of publications every year. There's a science article using the Argo data set is published every 16 hours. This is gigantic. Over 5,000 research papers and over 400 PhD theses have been published since 2002. So in the next few slides, I'm just going to talk about the value of the Argo data set and the use of it and why it's important. So this figure is showing an example of the use of Argo in ocean models. So the OSSIES, the Observing System Simulation Experiment, is just a way of assessing how important an ocean observation is and how much of an improvement it leads to in the results of the simulations. So this is showing two things. In the right panel, this is showing that If you if you compare assimilating Argo data that's the green line, to not assimilating any data at all, there's a very strong difference, and there's a large improvement in the simulations, in the predictions of temperature and salinity variability. But that's at large scales for looking at features that are evolving pretty slowly. And then the other result that is interesting is that when you're assimilating data, satellite data, you get to something that is highly complementary with the better simulations, but at this time for features that are faster at intermediate spatial scales. So another application of Argo is to look at how much of the ocean is warming. We all know that the ocean is warming, something that is pretty understood. And this top left panel is illustrating it. It's showing from the blue to the red the temperature anomaly of the global ocean from the 2000 to 2020. What we didn't know so far is how much of this ocean warming is actually extending to the ocean bottom depth. But we, thanks to the deep Argo floats that are capable of measuring temperature and salinity from the sea surface to the ocean bottom depth that can reach to 4,000 to 6,000 meters, this is now feasible. And these results are showing temperature record from deep Argo data collected in regional pilot arrays that had a lot of data collected in. And that's for the case of the Brazil, Argentine, and Southwest Pacific Basin, and all agree that ocean warming does extend to the ocean bottom depth. The last case here is showing the impact of ocean warming of sea level. So there's two facts that contribute to sea level rise, either and actually the contribution of both, the expansion of the ocean volume, and that's from ocean warming, or an ice melt. And what you can see here in the top left panel is a pretty nice closure of the observed sea level in black and the estimated sea level in purple up to 2015. But that's what's interesting is that starting in 2015, there was a misclosure of the sea level budget that has been observed. What are the causes for it? Well, the quick answer is that we don't know yet. A better answer is that different factors could contribute to it. There could be errors in satellite measurements, or there could be uncertainties in the way that we assess change in the ocean volume due to ocean warming. So a smart team from France looked at, okay, so let's assume for 1 second that the satellites are measuring sea level change correctly. And then let's estimate how much the deep ocean could contribute to increase of the ocean volume if we were to infer it from ocean satellites and Argo data sets in the upper 2,000 meters. And that's the blue line. And then the orange line is what's directly estimating from deep Argo data. And if you compare the blue and the orange line, you see a very nice consistency between the two lines. So this is only based on 2 deep Argo floats, so it's limited to a very small amount of data set, but this is very encouraging. And that tells us 2 things. First, that deep Argo is the technology that is capable of resolving deep ocean change in ocean temperature. And the second one is that if we were to increase deep ocean sampling, we would come to a better closure of the sea level budget. So I've talked about the value of Argo. Well, let's talk about plans for the future. So the expansions of one Argo are threefold. The first one, and I've talked about it, is to expand Argo profiles to the ocean bottom depth. The second one is to assess the productivity and the changes in the ecosystems, largely due to climate change, and that's by measuring biogeochemical variables from Argo floats. And the third is to expand Argo profiling to high latitudes in regions that are seasonally covered by ice, but also to double profiling in regions that are highly variable, including western boundary currents, equatorial regions, and marginal seas. So for that, we need 4,700 floats 1,200 of them would be deep floats, 1,000 BGC floats, and 2,500 would be core floats that would only measure temperature and salinity in the upper 2,000 meters. So where are we at right now? Well, let's go back in time just a little bit. In 2019, the One Argo design was articulated at Oceanops, and it was approved by GCOS and GOOS. Between 2015 and 2022, there were implementation of regional pilot arrays, deep floats and BGC floats, to define the capabilities and the performances of the floats and the sensor. So when will One Argo be implemented? That is the big question. So to fully implement One Argo, it is required 120 millions per year, and that's at the international level. Well, that can seem like a lot, but actually is not. It's actually comparable to the cost of a single sensor on a satellite Earth observing. So it is actually quite reasonable when you think of it and you realize that it provides you with the means of monitoring the ocean from top to bottom in real time. And given the strong impact that One Argo could have on improving climate and weather forecasting, it is urgent that One Argo is implemented globally. So, as I mentioned earlier at the beginning of my talk, I think it's useful to think of what made Argo successful, and the answer is actually quite simple. The Argo program is successful because it is international. Thinking for 1 second that Argo could be implemented just by one country is unrealistic. The Argo partnership plays a key role in the implementation and the sustainability of the global Deep Argo array, and it plays also a key role in the quality control of the data set. I talked about this earlier too, but I just have to insist on the fact that Argo's value is highly dependable on the unrestricted availability of the global Argo data set to the public, to the scientific community internationally. And then the third reason is that Argo is highly dependable on the strong connection between the academia and the industry. Academic scientists provide a fair assessment, unbiased assessment of how well the sensors and the floats are doing. They have the resources, the scientists that have the technological knowledge, but mostly the knowledge about ocean dynamics, ocean water masses, and can detect when the sensors are starting to misbehave. They also can provide supply for funding resources for Argo development and innovations. Those are resources that are not necessarily available to the industry. On the other hand, the industry covers the large-scale production of Argo floats and sensors, and also resolve the technological issues that are reported by the academic scientists. And then finally, a priority is for Argo to diversify the float and the sensor providers, because delays or interruptions in the production would have a very negative impact on the global array, because deployment opportunities are not necessarily, and most of the time, not available every year. So these are Argo's keys to success. I'm happy to take any questions.
Thank you, Nathalie. I'm going to hold questions until the end. We're planning on having the panel come up and do a joint Q&A session. So next up, Dr. Yi Chao.
That's good. Thank you for the opportunity to present here in the TMA event. And thanks, Nathalie, for this really nice summary for the Argo program. So my transition from academic researcher to startup company is really motivated by the Argo, as I working for NASA Jet Propulsion Lab, launching satellites, and I have been seeing the evolution, the companion evolution of Argo with altimetry satellites. measuring sea level from space. Argo take the third dimension and provide that missing piece of the subsea measurements. So I started my career as an ocean modeler at Jet Propulsion Lab, and then I worked 20 years and developed a particular technology, tried to enhance an Argo program, make them extend their lifetime, have more capability, carry more sensors, and then profile frequently to sample more synoptic evolution. So really transitioning my 20 years of research career as a scientist to a startup company, try to commercialize this technology and motivated by the successful Argo program. Continue to get funding from NASA, ONR, NOAA, partner with industry, as a previous speaker talked about, take public private partnership to make a successful transition. So I'll walk you through a couple of key points and then where we are in terms of we're still early stage a company, try to bring this technology to commercial application. Hopefully we'll benefit Argo and beyond. So as I said, I started with an ocean modeler. I continue to, I spent more than a decade working with IUs and SCUs and SENKUs and then AUs as providing forecasting models. And I officially retired October last month. Turn off my model has been running for 30 years, and now I'll take over as operational system, working with the round model. So that's kind of first chapter of my career as an ocean modeler. I spent 15 years to help launch the salinity satellite Aquarius. That's my kind of second highlight of my career. And I realized as study ocean from space, you can only catch the surface, and then wonderful Argo platform can really give us the full three-dimensional ocean information. As a modeler, I realized without data, a model is just a computer simulated numbers, right? So deeply realized the impact of the data, and Nathalie showed a similar graph. So the evolution of robotic and ocean application, and then really showed the takeoff of the ocean data from Argo, from gliders, from AUVs. Now we see this dramatic increase, order magnitude increase over the last decade or two. And I can see that increase is going to continue to increase in the next decade, take another one order, maybe even two order magnitude increase of data in order to have the sufficient data to constrain the models, making an accurate prediction from climate to the synoptic weather time scales and the ecosystem in the ocean as well. Nathalie showed this very nice program of the Argo. If not among the successful program, in my mind, is the most successful international partnership to bring this global observing system into bear. This is a summary of the challenges I started to get involved in this about 10 years ago, is how to extend the capacity of the profiling float as a good platforms. And then all these float are driven by batteries and with a limited storage. Once you launch the float as autonomous systems, and then you use the float to the energy to profiles, to collect sensor data, communicate with satellites. All of these every profile you make, you consume finite amount of energy, and then with a limited supply of the storage on board, and then basically have limited lifetime of the profile. So if you take the number of profiles of the percentage of Argo over 10,000 float being deployed, and then majority of these profile about 300, 200, 300 range. And basically the right-hand side show you the green dots is the float reporting data today, and then the red dots are showing the end of life of the Argo, because it's just because the battery are running out of power. So that's really the challenge we try to address, is to ask the question, can we recharge this battery in the ocean, take advantage of the infinite amount of thermal energy associated with temperature difference? Over 3/4 of the global ocean have this thermocline, have a sufficient temperature gradient, is warm in the surface, cold at depth. Henry Stommel proposed this 30 years ago in the Oceanographic article, saying the gliders and the float at that time, the Slocum, should be powered by the renewable source of energy, so they can profile as frequent as you needed to monitor the weather, you can carry as many sensors as you want, and then process the data, and then send the information back to the command center to be assimilated into models. So Seatrec has been working with a number of those pioneers, and then taking Henry Stollmo's idea, work with Ross Davis, Doug Webb, and then try to take advantage of these concept using phase changing materials. When they go through these profiles, you basically melt this solid material, which is solid and cold water at depth. You melt this material, expand in volume, and that's create a hydraulic pressure. If you put in the contained volume in the right-hand side, and then you create this very high pressure hydraulic force, and then you can spin the motor, generate electricity, you can recharge the battery. So every time you profile, not only you're not depleting your battery, but you're generating net positive energy. You can accumulate and then store those energy, and you can carry more sensors and doing additional computing. So it's really an energy neutral platforms. And then we started this about 10 years ago, collaboration with Ross Davis Scripps. I take the moment to acknowledge the contribution of his team, develop the float, and help us using Solo platform to do our first demonstration. So Kyle here, and Ross engineer at that time, and help us to construct a prototype. And this is the first 3 Solo float Ross built. And then this one of us customized with the thermal engine or the SIN tube around the floats. And this is funded by Office of Naval Research, Autonomous Systems. And then really demonstrated for the first time the Stollmo, the hypothesis can be realized in the ocean. You can deploy the ocean to profile, generate more energy than you need, and then to carry out the mission. So Seatrec kind of spin off after that demonstration as a startup company to commercialize this, go through the licensing with Caltech, and then start raising money, try to write SBR proposals funded by NOAA, by ONR, and try to mature this technology, make it ocean worthy. And then eventually we deploy about a dozen of these float in this middle column configuration, work with Seabird, Navis float in the middle. And then we provide this commercial grade energy power harvesting system attached to the third party floats. And then we're in the process developing a fully integrated float with based on the feedback from Argo, from the float customers. And they really want to miniaturize them and then create a cost-effective platforms with unlimited energy to not only to carry CTD and the biogeochemical sensors. We are starting to integrate active acoustic echo sounders to map the bathymetry, work with seabed 2030 to map the 80% gap of the global seafloor. And we just to kick off a project with Naval Postgraduate School to carry hydrophones. And now we have unlimited power is scalable. The more material we carry, the more energy we can produce. Now we can carry a Linux computer, try to process those acoustic data people can collect in the listening, and then try to distinguish the natural sound versus man-made sources. So a number of applications. We also talk about potential other sensors we can carry on this platform. We're looking forward to hearing your ideas and input. And I think the potential is unlimited. In addition to ocean mapping, there are potential to carry sensors to benefit a number of different blue economies, ranging from shipping to offshore operation to the wind farms, aquaculture moving offshore, carbon sequestration, and understand the ecosystem, the environmental impact of the operations at sea. So there's a number of different applications we have done so far. I'm looking for opportunities talking to you to learn about your ideas, what's your unmet need. If the energy is not a limitation, what you can do with underwater platform like a profiling float. Thank you very much.
Thank you. And next up, Paul Devine, Product Line Sales and Applications Manager from Teledyne Marine. And I can't wait for the Q&A, just like you.
The one with Paul Devine, that one. Yeah. Thank you. Can't really see anything. Okay. Hey, thank you, Carl. And thank you, BlueTech, for the opportunity to speak. Thank you very much. I've been thought a while about how to make this correlation between abstract science and powerful solutions. And my experience at Teledyne over the last 20 years, I really have seen a difference between the access to the raw data that's required for the academic versus the powerful solution where someone is really just looking for an answer. Give me the number. Is it green or red? And my name's Paul Devine, and I'm a member at Teledyne. I don't have a pointer here, do I? It's okay. So we provide solutions to a number of major markets. Energy, aquaculture, oceanography, water resources, civil engineering, hydrography, navigation, defense. We have a bunch of different product delineations. I'm actually associated with the imaging, acoustic imaging, bathymetry, and for the bottom classification, water column classification, and then the instruments. Is Shannon here? We have a member of the vehicles group here who's responsible for the unmanned and autonomous systems. But the way Teledyne is, just as a point of reference, the way that as we have acquired companies over the time, we've been acquiring technology. We've also been developing technology, but we've separated ourselves internally into three different main businesses. The business on the left is for connectors, cables, which are very important. All instruments need them. All vehicles need them. I'm a member of the instruments group where we're selling sensors, sensor solutions. There's also a vehicles group that's put together a package. We put the Argo floats into the vehicles group because it's a sensor delivery package. So I'm going to talk a little bit about the products that are made in San Diego and the products that are made in North Falmouth. But Teledyne's got a bunch of offices all over the world. Teledyne Marine is based in Daytona Beach. Teledyne Corporate is in Thousand Oaks, right? So Teledyne's much more, Teledyne Marine is only a small portion of Teledyne as a whole. But I personally sit in San Diego. Teledyne RDI makes the DVLs, Doppler velocity logs, and acoustic Doppler current profilers. We're in Poway, which is the city in the country, about a half an hour from here. If anyone wants to come up and take a tour, if you're here on Friday and you want to, I can let you in the back door and take you through manufacturing. But the application, from the first transition from abstract science to a powerful solution is I picked this example of the Oleander project. Has anyone seen The Day After Tomorrow, that movie? Anyone? Right? So the Gulf Stream, the theory was the Gulf Stream was going to be diverted over to Spain and the North Atlantic was going to freeze and send the climate into crisis. Well, back in 1990, early 90s, Stony Brook, University of Rhode Island, and the Bermuda Container Line, funded by ONR and NOAA and NSF, put one of our Dopplers onto a container ship that was doing weekly transects back and forth to Bermuda and measured, this is satellite altimetry or satellite ocean temperature. And on top of that, they have overlaid, those are velocity vectors, the length of the vectors, the speed of the current, the direction the current's going. And you can see the warm, dark Gulf Stream. That's New York, New Jersey. Anyone from New York? No? Nobody? Jersey? Anyone? No way. You're from Jersey? I graduated from Sunnybrook University. Okay. All right. So Charlie Flagg and Tom Rosby, I don't know, they took this on and they have weekly measurements of Gulf Stream transport. How much water is going from the equator to the North Atlantic? How much heat? They're doing XBT casts along the way. How much heat is being transported from the south to the north? And they were trying to answer the question: is the Gulf Stream going to shut down? How is the climate changing, affecting the Gulf Stream transport? And that line over there, it looks like the trend line is downward, but they said that wasn't statistically significant. But they were able to take all this data where they had asked us for access to all of the raw data, and they got into the nitty gritty of the performance of the ADCP, because this container ship's going 20 knots. It's like trying to measure the current it's like trying to measure the wind speed and direction with your head hanging out of the window. You measure the speed of the boat. You measure the speed of the car. So, we worked with URI and Stony Brook, and they got a good system running. But it was for academic purposes, and they really wanted access to all of the raw data. Then we get to a powerful solution. Not that understanding the Gulf Stream wasn't a powerful solution, but we took this same concept of the Doppler measuring depth, speed over ground, and current from near surface to near bottom. You can calculate how much water is flowing down a river. It's a transport measurement of river discharge. And we've taken the ADCPs, we've made them smaller, and we've provided, we've worked with Teledyne Ocean Science to provide packages, floats, and boats to deliver these ADCPs and get them across the river. Now to autonomous systems, bottom right, so that you can do a survey without having to put a person on the water and endangering them during a full flood. And what they're really interested in is this one answer, right? They hit the green button, they get a discharge, they go on to this next site. They're not really interested in all of the raw data that produced the answer of how much water is flowing down the river. And I think that, for all of you BlueTech startup, you're going to transition. Has anyone read Crossing the Chasm? Anyone? You read? So initially, right, you need to provide the scientists and the wizards of the world with access to all of the raw data so that they can work with you and develop a solution. And then you hide all the knobs. You hide the majority of the knobs. And you give the broad community the ability to hit the green button and get the answer. And that's to take it from, we saw a slide earlier, vessel mounted ADCP or vessel mounted surveys are going down as the autonomy increases. But as we go to more and more autonomous systems, we're going to need answers coming out of the instruments and the systems, not all the raw data, because telemetry systems are limited. Next example from abstract science, we mentioned Doug Webb. Doug Webb sold Webb to Teledyne in 2008. And this was a Lifetime Achievement Award, I believe, from Hui, as he was an ocean engineer at Hui before he started Webb. He still comes into the office. Was lucky enough to meet him. But he worked initially with Russ Davis to develop, it was mentioned earlier, to develop the first floats. And we have sold, I'm not personally in the vehicles group, so I don't deal with this product on a day-to-day basis, but I understand that we've sold 10,000 Apex floats. And there's only been 10,500 used in the Argo float program. I think we sold a lot of these to commercial firms. There are a lot of oil and gas contractors that deploy these for commercial applications, and the data doesn't go to the Argo database because they're commercial firms and they paid for it, and they're not data socialists like the rest of us. But 1,000 Slocum gliders as well, which was an offshoot from the float program. But the big focus recently, as we saw, is the biogeochemical floats, and that's a lot of the development of the biogeochemical float was really funded internally by Teledyne. The money, the seed money that we got from the federal agencies and was small compared to the time and the effort it took to develop it internally. So, we appreciate, I guess Carl or, the speaker from the Navy, Al, mentioned that, the commercial firms have really invested more than the federal funding, which I was shocked. RD Instruments' initial funding came from Office of Naval Research and NOAA, but this was recent developments at Teledyne RDI and at Teledyne Webb have all been internally really IR&D funded. So they're always asking the question, how many of these are going to sell? I don't know, at least at 10,000. So recently, the same group, the vehicles group, has put together this deep water AUV for surveying. You know, it's the deep water AUV kind of came out of the deep tow, right? So if someone wanted to search for a downed aircraft or do a deep water survey for resources, previously it was a towed fish with a cabled connection to the surface. And people want to cut the cables. They want autonomy. They want to be able to let the vehicle go and have it survey while they come over here and do something else and then pick up the vehicle at the end of the day and change the battery. But more importantly, they want a solution, right? I want a bathymetric map. I don't care about individual pings from a multi-beam. What I want is how deep is the bottom, you know, and if I put an environmental sensor on there, where did I see the spike in the fluorometer? So we've come to a full solution with the software solution as well. You download the data from the instrument, you get all the data with all the metadata, but then you also get a bathymetric chart at the end of the day. And I'm Paul Devine. There's my number if you want to call me. If anyone wants a tour of RDI, I'll pick you up and drive you up to Poway, the city in the country, on Friday. How'd I do on time? Good. Thank you.
Thanks. Next up, Leif Bildoy, product manager for Blue Insight Ocean Science from Kongsberg Maritime. Did I get your name close?
You did. Very good. This one. All right. My name is Leif Bildoy. I'm the product manager for Blue Insight, and we will do our little thing to get to the singularity. Maybe not today, but we'll provide some insights, I guess, over time. Most of you probably know Kongsberg. We are in 3 business areas: maritime, defense, digital. And one of the things is that we often find ourselves working across these areas, which makes it a very interesting place to be. So we operate from deep sea to outer space. And Kongsberg Maritime, we have 4 business areas here that kind of points straight back to the management of sustainable oceans. And myself and my colleagues here, we are in sensor robotics. So that's where we build the Hugiens and the EK80s and all the good sensors. We are about 7,000 people globally, and a whole number of countries. So, Blue Insight. Let's put these up. The new blue economy. End users, societies, we have some needs and some requirements related to ocean. And there needs to be a mechanism then, some services that will fulfill those and realize those needs. So how do you go about that? You start usually with observing technology, sensors, platforms, systems, navigation. Kongsberg Maritime is very known for operating in these, building world-class sensors and so on. But you need a little bit more. Around observations, we start talking about measurements, operations, deployments. I mean, you're probably doing a survey. You need some field services. And out of that comes data and data management. You need to think about how you handle the data, the types of data. You need to think about visualization, storage, etc., etc., and probably also sharing, because you're going to work in a community, maybe internally in your organization, and also probably with externals. So there's got to be some way of sharing. There's got to be some mechanisms around that, ensuring that all the security-related issues are covered. And in the end here, we end up with information delivery. We end up with predictions. We end up with analysis. We use machine learning, AI, not entirely to the level of the singularity, but we're getting there. And in the end, you get products, service deliveries that will help you then close these original needs and requirements that we had. And Blue Insight is complementing the very strong world-class sensors that we have from Kongsberg here. We are more in the information level, data and information, and managing data. So we're trying to figure out good ways of managing data, depending on what data you have. So if you just look a little bit on some trends in ocean observation, because it's kind of important, there are some drivers that drive us in what we're doing. So what we are saying is that there are more and more instruments, and customers typically need to operate a cluster of instruments, and together they will do the measurements, provide the measurements that they seek, and they do so with more and more vessels. So Armada is suddenly becoming a reality, concept of reality, and requires interoperability. And you need to start thinking about fleet management with more vessels, and they're often also smaller, USVs, AUVs, etc. Timeline becomes a issue. So we're moving from doing a sample, single sample in time, to more continuous mode of measurements. And those factors, well, they generate more data and higher volumes of data. And we need to think about how do we organize data, how do we collaborate, and how do we share. And one observation we see, of course, in Kongsberg, is a huge demands of AUVs, USVs, and in general, the expectation is that they're behaving and operating with a higher degree of autonomy. We're not fully autonomous yet. Mostly, you will see that there will be requirements around ROCs, remote operation centers, and so on. But it's definitely moving towards more autonomous vessels. And then time to market, it's important, and the requirements for time to market will basically challenge us on tech stacks. How do we build these information systems? Because we got to be able to deliver fast, deliver value fast to the customers. So the one big challenge here is to make the right ocean data available to the right people at the right time. Maybe it sounds a bit convoluted, but there are certainly some points here worth mentioning. It is so when we talk about data, we could maybe divide it up in two types: the data you have, the existing data, and the data you don't have, the non-existent data that you're actually going to collect on a survey, because managing those things are slightly different. And here we're trying to point out how do we collect real-time data and so on. There are some problems in doing so. It's very complicated setting up robust data paths from a sensor at the ocean. And collaboration, we know it's hard. We often find siloed data and many proprietary formats. The analysis of those data is manual, and that means it's time-consuming, requires specialist skills, and it's expensive also to put specialists out at sea in a research vessel. And now, as we said, there are more AUVs and USVs, and what you then find as a challenge is actually how do you remotely manage the sensor payload, and also you need to start thinking about the software on board those vessels. They might be running machine learning models, and how do you update those? That's all very complicated. So we set out, I think it was last year, we launched Blue Insight. So that's a platform to manage ocean data and offers key value to a number of stakeholders. You might initially think that all of these are quite different and would have very different needs, but there is actually a common set of needs that basically span these, whether it's aquaculture, and we certainly see a lot of that aquaculture interest up in Norway, fisheries, and same energy production. Could be oil and gas, but it could also be offshore wind, more and more so. We work with government authorities and researchers as well. So it was pointed out here earlier that the sort of might be a little difference in how you use a product in this space if you're academia, researcher, or an industrial player, and you might want to do some research post-mission, but it could be also use cases where you're doing decision making on the spot out in the ocean. So it's quite a span. So that leads to what are the jobs to be done in ocean observation, and how does Blue Insight try to support that? So you may want to collect some sensor data and transfer it securely to a cloud. You may want to integrate third-party data, and you want to effectively increase the understanding of the ocean space by then using third-party data. You may want to manage sensors and data flows, important as well, and to ensure efficient processes. You may want to analyze data in real time at the edge or post-mission in the cloud. It could be a mix of this or either or. We see different use cases around analysis. And further to that, you may want to predict relevant variables in an aquatic ecosystem, and it might be on the fly to guide business decisions. Most likely, you would want to visualize data and insights, and you might think about 2D or 3D, and you may also want to require customizable dashboards because we probably have all different needs. And you may want to contextualize the visualizations with application-specific content and mission-relevant references. And finally, you may want to share in blue here, your blue data and insights, or simply distribute raw data under FAIR principles. So sometimes you have some of these areas, Blue Insights, or you have all of them, and Blue Insight try to accommodate as much as possible around that. So here's a little diagram about the system overview. And you can see in the bottom here, there's some different vessels, a Drix, sounder, a research boat. You may have some Kongsberg maritime sensors. There might be a third-party sensor. There might be a KM database, third-party database, depends how you're set up. And generally, you want to have a data acquisition layer as the first thing you think about. How do you collect the sensor data and make them ready to be pushed up into the cloud in a secure way? So then you got a cloud service. You may want to visualize some of that data. You may want to run some analysis and straight on share it. It could be simple as a forwarder, forwarding data to a third-party database. But you might also want then to run a remote control of the sensors. And I called out also here, one thing we see a lot is edge classification use cases. So we basically built an edge compute capability around Kubernetes and Docker containers, same as running in the cloud, which makes it very easy to push workloads where you need them. So if you need to do compute job processing on the edge node, you can do that. You're closer to the raw data and higher quality data. So if you have bandwidth constraints, it might be very wise to classify data closer to the sensor. So then I'm going to show you some screenshots here of the environment of Blue Insight visualization. Here we see some ice ice cap marked out. It might be interesting if you're operating a USV to know where there is ice. This is the oil field ecofisk with some security zones. There is a AIS management bounding box rectangle there. You can choose which vessels you track. We can visualize underwater environmental measurements and biomass classification. So we see some ecograms as 3D curtains zooming in and applied with the classification. Believe it's plankton here in blue. And then short little video of the 3D rendering. You will see a sailboy. There's a lot of tracks you see in the ocean here. There are some boxes which represents the measurements that's taken. We get to go and see the ecofisk, oil installation, and I believe we jump over to high wind, see some wind turbines, etc., etc. So very powerful 3D rendering engine. I said earlier we work across the different business areas. This is actually a capability that is built by Kongsberg Digital that we're using in Kongsberg Maritime for Blue Insight. So that's very helpful for us. And then last slide. So a little bit about the benefits in Blue Insight. We improve the efficiency. We try to help in collaboration between colleagues and communities. And Blue Insight is an open ecosystem, no vendor lock-in. Parts of this is open source. Other parts are not. But that's decisions we take when we build products, etc. So that's all. Thank you.
Sorry, speakers, could you come up to the panel, please? And I think, let me get the mics turned on. So, Nathalie has to leave within 15 minutes, so I have so many questions for the panelists. So we're talking about the research to operations chain of events, the taking technology and observations and moving them towards societal benefit. And we've heard 4 very interesting talks in various different points of the scale. I've got lots of questions myself, but I'm sure you do too. I guess please maybe come to the mic if you have a question, or raise your hand and we'll try to bring a mic to you, or I'll call on you and repeat the question. Does anybody have any to kick us off, or do you want me to get this going? Yeah. And maybe introduce yourself before you ask the question.
On biogeochemical Argo, deep Argo, some of the new battery technologies, and how we can replicate that other technologies are natural.
Just tap it once on the bottom.
Got it. Okay, so I guess the question is so I described Argo's key to success, and the question was how to apply it to other observing system, or was it how is Argo planning to go about with the expansions? I'm not sure.
Yeah, how has the research been accomplished with so many different researchers working in many different countries to bring together a whole program? And how can we replicate that through the other technologies that would benefit from those international collaborations to all do something great together?
Requires a lot of work and patience. I guess is the short answer. So I think an important point is that it's just unrealistic to think for 1 second that you can implement a global observing system with just one nation. And I think the contributions of the different international partners has been implemented quite organically, based on the fact that people tend to deploy floats close to home and when they have opportunities for deploying them. So, and it's not necessarily close to home, but it happens in most cases. And I guess there's some exceptions to it. So, for instance, for Scripps, we have strong ties with New Zealand. And so, a lot of the Scripps floats deployed are from New Zealand ships, and for that reason are deployed in South Pacific and the Indian Ocean. So, yeah, and I think in terms of research, I think that's another part of the question. So it's just a matter of just collaborating, you know, and having the tools for maintaining an efficient and friendly communication between the different partners. And after doing that, the Argo program has multiple and very regular meetings every year. We have Argo science workshops. So I would say that communication is key.
Nathalie, can you say a little bit about the change management with that community? Because there's an agreement on a standard set of instruments and processes that's internationally agreed to. So how do you take advantage of what the companies may bring in terms of technology advancements that we heard from today, and all three types that we just heard from, with regard to that being a program that everyone's agreed to internationally?
Okay, so and I think I speak for all the industries that have the that are interacting with us. I think we're a friendly bunch, but we also have requirements that are very well defined. And there are, I think the requirements for the floats and the sensors are very well documented. And it's something that is, I think, very useful to have, to be very clear about the accuracy of and the performances that you need from the industries for the floats and the sensors. And during the meetings that I talked about, both the data management team meetings and the Argo steering team meetings, we make sure to have a specific days that are attributed to collaborating and talking with the industry and making sure that we can communicate our requirements well and they are well understood. We also make sure that we maintain the communication for telling them about when floats or sensors are starting to not behave well. I think that I mentioned that at the talk. And so that's coming from academia to the industry. And then from the industry, I think we are very lucky to contribute with industrial partners that maintains transparency. They let us know, and they are, I think, quite honest about limitations of the floats and the sensors, and letting us know of, ways that they could be improved. And I think projects like the NOPS, the partnerships projects for innovating and improving the sensors, and something that academia can help the industry with, to have those resources and those funds for doing it, is playing a key role in it.
Thank you. So I was going to ask Yi Chao a question, and then maybe also Paul and Leif, in terms of joining the activities of programs that exist and building capabilities to bring new technologies to bear. So sort of along the lines of that question for you, Yi, your years of experience on your slides, how is that going in terms of trying to build and bring in change to something that's already extant, already in existence? And for Paul and Leif, as a public good funder from NOAA who's trying to provide services for societal benefit and open data, how do we meld and blend with your companies to allow you to have competitive markets that you're trying to fill, but also open source data is something that has to be in the mix from my perspective. So how do we mix those together? Go ahead, Yi.
Yeah, I just want to summarize it, and I certainly is challenging. I think if you need one word reply, is spend 20 years as a scientist, now thinking about cash flows and then product market fit. Do you have the right team, and then how do you raise the next round and so forth? When I started kind of very little help available in the community. But I think we are really fortunate to have this event like this, TMA. We joined TMA 2019 shortly before the pandemic, and there's a CDL in Canada focused on the ocean. There's multiple incubators in Start Blue, in Scripps, and Mississippi, Boston. So now you have a lot of groups and then organizations helping people like me to transition. I wish those organizations have a strong presence 5 years ago when I started. So that's point number one. Point number two, there's a lot of resources available from both government and foundations. So we are very fortunate to get philanthropic support early on, both from Thiel Foundation and the Schmidt Foundation. SBR from NOAA, from ONR are instrumental to help us to pay the R&D costs, so we don't have to raise a lot of private capital to cover our operational R&D budget. And then you have to go out to raise money to do the commercial because the government money cannot be used for the commercial activities. So a lot of multitasking and then, but it's really exciting. I think I can write 50 more papers before I retire, but I think I can make a bigger impact by serving in the middle to transition from academic to commercial applications.
And audience, please keep bringing questions if you want, but I asked the daisy chain one to keep the conversation going. So Paul, how do you make your private sector meet your profit motives within that realm, and what are the recipes for success for partnering with us in the public sector with open source data from the capabilities you're bringing to bear?
So in terms of the profitability, right? Is that
well, how do you meld the two for those? As I watched your talks, I was struggling with a constant challenge I face in this world as a public servant. We're trying to provide public services that are, in essence, equitable services across societal needs and not just those who are able to pay. And so if a for-profit institution organization needs operational support for oceanographic data and information, and you can provide that to them and make profit, that's good. And I guess and we are funding with government resources some of your products and your capabilities to be in the mix with us, with partners who are deploying them and gathering data and making the data and information, as you mentioned, trying to get to that red or green button or go or no go. And some of those are profit-based opportunities for you and some are nonprofit.
Yeah, we are a commercial entity, and we do have stockholders, and who has a retirement fund, right? Who's a retirement account, right? So everyone wants the return on their investment. And it's a challenge when the oceanographic industry is very conservative and slow to change, where our initial products that we provided in the 80s are still working, and people don't want to change. They don't want the new product. So the return on investment for our R&D is always a lot longer than the stockholders are interested in waiting. So it's been a problem when you invest in a new product and you release it, and your old product continues to outsell it 3 years later, because NOAA doesn't want to change, right? Because the NAVO is happy with what they have. It ain't broke. So a lot of just getting back to data, then it was a two-tiered question. The goal is to always store all of the raw data to satisfy the academics and the wizards that are looking at the data. And the challenge is to provide meaningful summary output for transmission in real time to shore. So that's the challenge, is to provide meaningful answers in real time, because everyone wants it now. They don't want to wait for 6 months to download the data anymore. That's a big change in the last 20 years.
And I didn't mean to make a hot seat if I did, and thank you for that answer. But that's part of what I think through this is, how do we innovate faster towards the solutions? And it's how to use the tried and true without breaking it, and then enable the new at the same time.
Yeah, and it's I was amazed at how conservative this industry is in terms of not wanting to adopt newer technology because what you have already is almost good enough. You need someone like the funding agent to say, thou shalt produce data results in real time, to force people to deliver the data back to the beach and to force them to adopt the new technology. I'm not going to fund you unless you provide a better solution or a better answer.
Leif, do you want to weigh in or offer?
No, I've seen some of the same things as Paul talked about here, but I think in the end it depends. And because are you going to collect all the raw data, or are you just going to take the classified data, which is much simpler, and push it up, less bandwidth? The answer will not be the same for everyone. And I think what we need to do then is to provide frameworks, tools that can cover a huge span of use cases for this. That's yeah. And so I'm thinking like in terms of so collaboration to help on collaboration, tools like APIs. We know how to pick up a phone and call each other, but how do you make the systems connect? There are established paradigms for that around APIs. In Kongsberg, we think about APIs everywhere as a mantra. Everyone should do that. We see ourselves as helping with tools for collecting and managing data. We do not gobble up the data as if it were Kongsberg Google for the oceans. We believe that our customers decide who they share with, when and at what time and what type of data to share. Because it's very important that all data is not equal. Some should probably not be shared.
Yeah.
It's not real time.
Right. So I had another question from the audience.
I think I also find that in teachers' voices as well. A follow-up to the comment of speaking from Teledyne. You said that some of your customers have reticence to produce data in real time. They don't want to invest. They don't want to do it. That's why. Is it a concern about data integrity, cost, or something else?
I think the degree of difficulty goes up and the cost goes up. If you want the information at your desk in real time, it's much more expensive, and the number of points for potential failure along the way increase.
I presume though that Teledyne provides an economic analysis along with this. The benefits of data are so great. I would think that they would often outweigh the cost or something like that, particularly real-time data.
Well, I mean, and a lot of times we're just providing a sensor that's part of a network, and we provide sensors only to groups that will deploy it in the ocean autonomously on batteries and then visit the site 18 months from now and download the data. And so I think it's about a 10x increase in cost to get the information back to your desk in real time, to get it to a satellite and back to the beach. You know, from the sensor through the data logger to the satellite and back, as opposed to just residing inside of the sensor.
I think there's another point to it, is that when you return data, you have to make sure that it's actually acceptable. And it's a lot more difficult to provide data in near real time that is quality control partially, that has an automated system to make sure that the data that you send and share with the community can be used and is valuable. When you have 6 to 12 months to have a look at it, you know, it's much easier. I'm not saying that it doesn't take a lot of time. It takes a humongous amount of time, and it takes resources, personnel. What I mentioned during my talk, people have knowledge about ocean dynamics, who have knowledge about water masses, you know, to make sure that the data is actually good. But in near real time, you have to have an automated system that does it very quickly to filter out what data should not be used and should not be shared.
Was it? Go ahead, Clarissa, and then maybe. Yeah.
First of all, I want to say 4 fantastic presentations, all well organized and very, very informative. I want to make my own ocean observation that in 1973, I was at University of Hawaii getting my first master's in an oceanographic study of the University National Oceanographic Fleet needs for 1990. And I predicted at that time that professors would be at their desk, have global communications to what was equivalent of an IBM 360 on board the ship, and there would be a tethered down manned vehicle, and there would be a pilot that would take readings and make observations and then send them back to the professor in real time. And I had another professor that said you could spend your entire career using today's technology to solve yesterday's problems. That was 50 years ago. Think about where you're going to be 50 years from now, and just remember that lesson. Look to the past and predict the future.
Clarissa, did you have a question?
Thank you, Carl. Hi, Clarissa Anderson, the Southern California Coastal Ocean Observing System. I was just thinking about what you were just saying about how it costs 10 times more to do real time. If that's the case, I am not charging enough through the IU system. We do this on a daily basis. We do everything from real time to delayed mode at an incredibly low cost, end to end, to the cloud, to the products, to the visualization. So I just want to push back on this idea that this is so costly because we're doing it at just bottom of the barrel prices through IUs. And to the point about delayed mode, this is very important. We actually apply all of the flags in real time to our data they're going through. They're not perfect. We then put QC'd versions out in delayed mode. Sometimes it takes 6 months, sometimes a year. We have plenty of caveats on our websites explaining that there are going to be spurious results, say in chlorophyll because of biofouling, et cetera. So I'm just not yet understanding the grand challenge here, because somehow we've managed through the government funding that we get, which is quite low compared to what you see in the private sector, to do this stuff and to do it at climate quality scales. So I don't know if I have a question. I'm just a little confused about this metric of 10 times more, because somehow that's not translating to the sensors we have at Piers, our glider work that we're doing, fully through satellite telemetry, our radar work. We do not have that kind of a cost difference between all of these things. And I don't know, maybe you know my system. Maybe you can speak to this, because I think you have insights from both sides.
Yeah, I think some of this real-time. Hello? Yeah, some of the real-time transmission, because of the platform intrinsically is not in the upper ocean. Like glider and float, they can easily come to the surface, get the data through Iridium network. A lot of the, deep ocean platforms, they are anchored, they sit on the bottom, and they have no easy mechanism to transmit data, because the tripod cannot rise to the surface and it's done, right? So you have to sit there for 6 months or 18 months. And then when the ship next cruise go there, retrieve the data. I think we need to look for new technology to reduce that 10x cost. And there are many ways to send bubbles to messengers to the surface, data messengers. We talk about marine geologists at Scripps, using our profiling float tethered to the, you can rise to the surface and then go give you every week. And then before you lost your instrument, you lost the data. So I think when you talk about 10x cost increase, it's time to look at new technology, new innovation to solve that problem.
And I'm going to pass it to Leif, and then I might go back to you, Clarissa, with the challenge question. For me, when we're talking about these things, I'm trying to identify what are the barriers to success for collaboration across to accelerate the solutions. And so maybe it's in what I think exists in uptake of new is the people time to come up with a level of QA/QC that's acceptable at first, to name it, call it with the caveats, and then move to a new version and identify that gap as a skill gap right now that you want to improve. And you can react to that after I hand it to you.
Yeah, so just a comment on this. I mean, on the bandwidth thing. Satellite communication is expensive and the coverage is poor. Now, it's not, we challenged here to think about what happens in 50 years' time. 20 years ago, I worked in Nokia Research Center and tried to implement real one player into the Symbian platform. That was painful. At the time, telecommunication operators would pick the 5 MTV videos you were allowed to see on your phone, and it barely worked. So we are making progress. It's evolution, and 20 years from now, I mean, we already see Starlink and things like that. There will be more of that, and that means costs will be coming down. You can transfer more data, etc. But it is a challenge today, for sure.
So we're about at time. Clarissa, did you want to make a final comment?
No, it's okay. We can have an offline chat.
Okay. So with that, one of the things TMA BlueTech does is give us long breaks. I've taken a little bit of ours because we started a little bit late. So I'd like to basically say, help me to give a big round of applause and thank you to our panelists.